All right, guys, let's start. So now we are doing your another topic, which is called numerical analysis. Chapter number 1 is about your introduction to numerical methods in finance, and in chapter number 1, we are doing your lesson number 1, right? So again, numerical analysis means that using computers and approximations methods to solve your mathematical problems when an exact formula is unavailable or impractical. In finance, many problems are too complex for a closed form formula. For example, Black-Scholes has a neat formula for a plain European option, but once you move to American option, barrier option, part dependence, stochastic volatility, trade portfolios, or your multi-asset derivative, exact formula often kind of disappear. So numerical analysis becomes the practical engine behind your quantums. Okay. So if your financial problem is option pricing, why numerical methods are needed? Because many products don't have closed form formulas. If you're looking for portfolio optimization, real constraints make the math very complex. Risk management, war, conditional war, stress testing requires simulation. Interested modelings, models like your Hull White need trees, PDs or simulation. Credit risk, portfolio loss depends on your correlated product. The main idea of the lesson is very simple. In finance, we cannot solve the model exactly, so we approximate. We must understand how accurate that approximation is. Okay. With that, let's kind of get to the next slide and try to dig deeper. So now here, right? Here we'll try to understand the introduction to your numerical methods in finance. We'll have some overview. We will look at your key applications in finance, key advantages, and what we're going to look ahead, right? So again, this is the core overview slide. The slide says numerical methods are computational techniques used to approximate solution to mathematical problems that cannot be solved analytically. What does analytically mean? Analytical solution means a clean formula. Example, very simple example, which you have seen, the Black-Scholes formula, call option price is equal to S naught and D1 minus K exponential minus R T and D2. Okay, this is the Black-Scholes call option formula. It gives the answer directly, but many problems do not have such a neat formula. Then what? Then we use the numerical method. The application in finance, first one is option pricing. In options, we often solve your equations like the Black-Scholes PD. A simplified Black-Scholes PD is given for option price. Simplified Black-Scholes PD is given in this format. You've seen it already. Okay, partial V by partial T plus 1/2 sigma squared S squared partial squared V by partial S squared plus RS partial V by partial S minus RV equals 0. Meaning V is the option value, S is the underlying stock price, sigma is the volatility, R is the risk-free rate, sigma, your partial V by partial S is delta, your gamma is also there. If the option is simple, we may have a closed form formula, but if it's complex, we solve the PD numerically using finite difference method. Another method is portfolio optimization. Portfolio optimization asks you what should I or what weight should I allocate to different assets to get the best return for a given level of risk. A classic mean variance problem is your what does this mean? Basically minimize W transpose sigma W subject to portfolio expected return being at least R. Okay. So subject to at least R and all portfolio weights, right, summing to 1. Okay. So you have W, which is portfolio weight, then we have sigma, which is covariance matrix, mu expected return, R is the target return. In real life, constraint makes it difficult. Real world constraint is no short selling. Example is WI greater than equal to 0, max position, no stock above 10%, sector limit banking, max 25%, liquid limits, avoid illiquid asset, transaction cost, reduce turnover. So numerical optimization is used. Risk management, again, risk management uses numerical methods heavily. For example, Monte Carlo simulation is used for war value at risk ask, what is the maximum expected loss over a given horizon at a confidence level. So that is what we also trying to find out. Monte Carlo generates thousands or millions of possible future market scenario and calculate your portfolio losses in each scenario. Then we have interest rate models, right? Interest rate models such as your Hull White often need numerical methods. A basic Hull White model, if you have halvite model you have, that is your okay. DRT equals theta of t minus ART minus DT plus sigma DWT. Again, RT is short-term interest rate, theta t is the time varying level fitted to yield curve, A is mean reversion speed, sigma is rate volatility, DWT is Brownian motion shock, used for pricing and interest rate derivatives like options, swaps, floors, convertible bond. The overall big idea which is coming out from this particular slide is that if you're looking at, let's say, option pricing, numerical methods are used, PDE trees, Monte Carlo. If you're looking for portfolio optimization, you have optimization algorithms. You're looking at risk management, simulation trees, and stress testing. And you have interest rates, fees, PDEs, Monte Carlo, right? The slide is clearly telling us that numerical analysis is not abstract math only. It is machinery behind your real quant finance models, right? So now we will study core mathematical techniques, including root finding, optimization, algorithm, finite difference methods, and Monte Carlo simulation used across financial models. Okay. And advantages you can see here, right? Ability to model realistic multi-factor financial system, flexibility to handle complex payoff and constraint, fast enough accurate approximation for real-world decision making. Then we get into the next part, which is again we are looking at your floating point precision and computational accuracy, numerical precision and errors. Again, in computational finance, numerical precision plays a very critical role in the reliability of model outputs. Computer use floating point arithmetic to represent real numbers, which reduces approximation error due to limited precision. Floating point representation are basically numbers are stored as a mantissa multiplied by a power of 2. The right allows representation of very large and very small number. Exact representation of most real numbers is not possible, right? So slide introduce a very important but often ignored topic that computers do not store real numbers perfectly. In mathematics, we have 1 by 3 equal to 0.333333 infinite time, but a computer cannot store infinitely many digits. So it stores an approximation that is a floating point representation. So a number is stored roughly like x is equal to, let's say, m into 2 exponential, right? So x equals m times 2 to the power of e. M is called your mantissa, which is significant, the meaningful digits. M is called mantissa, significant, and the meaningful digit, 2 raised to power exponential, power of 2 that scales the number. So let's say if my number is 123.44, right? So I'll write 1.2345 into 10 to the power 2, right? Computer use base 2 instead of base 10. And why does this matter in finance is very simple, because model output is often priced by Approximate because small pricing errors can affect your large books, delta, hedging error, gamma, convexity risk, VAR, capital estimate, CVA, FVA, valuation adjustment, portfolio weights, allocation decisions. Suppose a bank prices a derivative incorrectly by only 0.02 per unit. If the notional is very large, the financial impact may be huge, right? And there can be a rounding error also, right? So these are the challenges in floating point arithmetic, rounding error, loss of significance, right? A rounding error occurs because the computer has finite digits. Example, 1 by 3 is equal to 0.3333. The exact value continues forever, but we cut it off, right? In finance, this can happen in Monte Carlo simulation, and millions of small calculations are repeated. And there is loss of significance also, because this happens when we subtract two heavy equal numbers. Let's say 1.0001 minus 1.0000 is equal to 0.001. This answer is small, but most of the leading digits cancel. This can be dangerous in finance when calculating Greeks using a finite differential, because, for example, we are calculating your, let's say, numerical delta, right? Numerical delta is approximated equal to value of your S plus H minus value of S minus H divided by 2H, right? So pronounced as delta is approximately V of S plus H minus V of S minus H divided by 2H. If H is too small, then Vs plus H and Vs minus H are almost equal. So subtracting them can create numerical precision issues. That is what. And then we have error analysis in numerical method, truncation error, round off error. Errors can propagate and accumulate through iterative algorithm, absolute versus relative error, absolute error, relative error. So the idea is the slide explains the main source of numerical error. There are two major types: truncation error and round off error. Right? Truncation error means truncation error happens when an infinite or continuous process is approximated by a finite one. For example, let's say we have Taylor expansion, right? So exponential x is equal to 1 plus x square by 2 factorial plus x cubed by 3 factorial, right? Plus so and so. So if you stop after 3 terms, let's say exponential x is equal to 1 plus x plus x square by 2. The missing terms creates your truncation error. In option pricing, truncation error appears when we discretize time. Example, binomial trees, a continuous time stop process is approximated using finite step, one time step, two time step, three time step. If you use 10 steps, the approximation is rough. If you use 1,000 steps, it becomes more accurate, right? And then we have your round off error. Round off error comes from limited machine precision. For example, let's say 0.1 plus 0.2. In many programming languages, this may not be exactly 0.3 internally because 0.1 and 0.2 cannot be represented perfectly in binary. Okay. In finance, round off error matters because if you are in a situation where Monte Carlo with millions of parts, why it matters? Because errors kind of accumulate. Iterative solvers because each step carries previous error. Matrix inversion because portfolios covariance matrix may be unstable. Recalculations because small bump cause subtraction issue. And there is kind of error propagation also. Error propagation means an error introduced. And your example in risk management is volatility estimate has small error. Option prices use volatility, delta and gamma use option price, war uses reach, capital requirement uses war, right? So one small input or numerical error can flow through the entire risk system. That is why model validation teams check your numerical stability, right? And then we have your, all these things, right? And we have your absolute error, which is difference between exact and computed value, also relative error, absolute error normalized by the exact value. So all these things will flow ahead. Also, I've explained you a lot of these things, right? So in fact, see, this is the truncation error, round of error, which I already discussed. A central aspect of numerical analysis is understanding the error that arise when exact mathematical problems are approximated numerically. The error can significantly affect the accuracy of financial model. I explained you in the previous slide. Occurs when an infinite process is approximated by a finite one, truncating a series expansion or time crystallization. Arises due to finite precision in computer arithmetic. 1/3 cannot be exactly implemented in binary. Error propagation. Error produced at each computation step may accumulate. Iterative algorithms are especially sensitive to propagation. Understanding propagation is crucial for model reliability. So that is important. Okay. Then we get into your error matrix, right? Error measurement and financial example. The slide gives two formulas, your absolute error and relative error, which you saw in the slide number 3 also. Absolute error is what? Absolute error is your equals the absolute value of x exact minus x approximate, meaning how far is computed value from the true value. Example, exact option price 100, approximated price 98. Expected value of your absolute error is 100 minus 98, let's say 2. The absolute error is 2. Then we have relative error also. Relative error is expected value of, so you can write it like this, right? So you want, right? So write this, and you can write this as like this, right? So relative error equals absolute error divided by the absolute value of x exact using the same example. 2 by 100, 0.02 is 2%. Relative error tells us the error in percentage term. Why relative error is often better? Because we have two pricing error, exact value 100, approximate value 98, absolute error 2. And then we have, let's say, 1 million, right? Approximate values 999,998. Absolute error is 2. Same absolute error, but very different importance. Rupees 2 error on a 100 instrument is meaningful. Rupees 2 error on a 10 lakh instrument is not at all meaningful, right? So keep that in mind, right? So absolute error and relative error are very important concepts when we look at error metrics, right? Error metrics when they have to be studied, especially in finance, right? Truncation error arises in binomial tree, option pricing, rounding of error affect your Monte Carlo simulation with many paths. Small numerical errors can lead to mispricing or incorrect risk estimate. So truncation error, binomial trees with too few time steps, round of error, Monte Carlo with many paths. Propaganda error, Greeks used in war. Error formula is not academic; it is directly affecting your pricing, hedging, capital, and risk decision. Okay, so that is what we need to understand very, very clearly. Then we get into the next part, which is your understanding of your basic numerical algorithms, finance, core algorithms, and implementation. So basically, slide introduces the major algorithm families used in quant finance, right? So the slide lists root finding, numerical integration, linear system, and you have Newton-Raphson method also listed here. Okay, so root finding means solving. Solving means fx equals 0, right? Pronounce such x such that f of x equals 0, right? In finance, root finding is extremely common. Let's say implied volatility, when we are trying to calculate, Blackwell gives you option pricing volatility. Black-Scholes, we have what, right? The call option is equal to Black-Scholes SKRT sigma. But market gives us option price C market. We need to solve for sigma, right? So what do? We give us BS SKRT sigma minus is equal to 0. So define your F sigma is equal to Black-Scholes sigma minus market. Then solve for your F sigma. Solve for F sigma. Okay, this is your root finding problem, right? Then we have your bisection method also. Bisection is simple and robust. Suppose we know in bisection, what do we do? Suppose we know f of your a less than equal to 0, right? And f of b greater than equal to 0, right? When the root lies somewhere between a and b, we take the midpoint c is equal to a plus b, right? We take c is equal to a plus b by 2. Okay, then check whether the root lies in your a or c or c or b, right? So root lies a or c and keep halving the interval. Advantages: very stable, limitations, slow, finance use, implied volatility, yield to maturity solving, requirement, finance, must change sign over interval. Then we have Newton-Raphson method also. But Newton-Raphson is faster but less stable because your x n plus 1 is equal to x n minus f x n divided by f dash x n. Xn plus 1 equals xn minus f of xn divided by f prime of xn. Xn is current guess, xn plus 1, next improved guess, function of xn, function value at current guess, f dash xn, derivative slope at current guess. Again, if you look at financial example, let's say the same example which we discussed earlier, right, which is f sigma equal to bs sigma minus c market. F dash sigma we can find out, right? Here we are using the same thing, but we are finding out f dash sigma, right, which is your vega. So Newton-Raphson becomes your what? Newton-Raphson becomes your sigma n plus 1 is equal to sigma n minus your Black-Scholes sigma n, right, minus market vega sigma n, right? So basically sigma n plus 1 equals sigma n minus Black-Scholes price at sigma n minus market price divided by vega at sigma n. This is one of the most important practical formulas in option market because bisection gives us bisection has strength, robustness, weakness. It is slow. Finance use cases, implied volatility, bond yield. Newton-Raphson is strength is fast. Weakness, it can diverge. Finance use cases, again, implied volatility, calibration. Numerical integration, strength is handle expected value. Weakness is approximation error. Finance use cases, option pricing, and risk neutral valuation. Linear solver, strength is solve the system. Weakness is matrix instability. Finance use cases, PD, portfolio optimization. So numerical integration, approximate integrals, general integrals, when we have, let's say, integral of your, a to b, your fx dx, right? So integral from a to b of f of x dx in finance, many prices are expectations, so such as your v is equal to minus exponential rt, right? This is the payoff, right? And this is a risk neutral payoff, right? V equals e to the minus rt times the risk neutral expectation of payoff. If the expectation cannot be computed exactly, we approximate it using numerical integration or your Monte Carlo, for example, option pricing. The role of integration is discounted payoff. Application bond pricing, role of integration, integrating cash flow, discount factor, risk neutral density, recovering price from distribution, Fourier method, pricing via your transform integrals. Then we have linear system also. Linear system appears in very simple things which you have seen in school also. Ax is equal to b. A is the matrix of coefficient, x is the unknown vector, b is the known vector. In finance, this appears in your finite difference method. For example, solving your PD, grid values, portfolio optimization, covariance matrix operation, risk model, factor exposure system, your curve construction, bootstrapping, yield curves, etc. Right? So that is what we have. Then we get into your summary of the numerical methods in finance. The slide basically summarizes what we have studied till now, or the key takeaways. The key points are numerical precision matters, errors come from a truncation and round off. Errors can propagate. Absolute and relative errors measure accuracy. Numerical algorithms are essential in your finance. The real finance connection is if you're looking for a concept called floating point precision. It affects your pricing and agrees. If you're looking for truncation error, it affects your binary trees and finite differences. If you're looking for round-off error, it affects your Monte Carlo and iterative algorithm. If you're looking for error propagation, it affects your VAR, CV, and stress testing. If you're looking for root finding, it affects your implied volatility and bond yield. If you're looking for numerical integration, it affects your price expectation. If you're looking for linear system, it is affecting your PD, pricing, and portfolio optimization. The slide is basically saying that numerical methods are not just coding techniques that determine whether financial models are reliable or not. In banking, asset management, and risk management, this matter because model output effect. Let's say if the decision in trader pricing, model output uses option value, model output is used in option value in the Greeks. If your decision is hedging, model output uses delta, gamma, vega. If you're looking for risk capital, model output uses VAR expected shortfall. If your decision portfolio construction, model output uses optimal weights. If your decision in treasury or the asset liability management, model output uses interest rate scenarios. If your decision is model validation, accuracy and stability checks, right? Model output use, right? So this is quite interesting, right? Numerical accuracy is critical for reliable financial modeling. Poor error control can lead to mispricing and incorrect risk assessment, algorithm choice, and decision management directly affects model quality. Looking ahead, we'll build on this foundation to study advanced numerical techniques and their application to financial modeling, including option pricing, risk management, and simulation-based methods. Okay. Then we get into your practice problem. The practice sheet focuses on numerical precision, error analysis, basic numerical algorithms commonly used in quant finance. So this is good because the lecture is not trying to make you memorize your formulas. It is wants you to understand, right? So when a computer gives number, how much can we trust it? That's the key practical question in your quant finance. Okay. Now we have the first question, floating point precision. All of the second question, just listen to the answer. What is rounding error? Basically, rounding error is a small error created when a computer stores a number approximate instead of exactly, let's say 1 by 3. 1 by 3, we know that, right? 1 by 3 will be 0.3333333, right? So computer approximation will be what? 0 point, maybe 4 digits, right? 0.3333. This difference is rounding error. Why does subtracting nearly equal numbers cause loss of precision? Because leading digits kind of cancel. For example, I have your 1.0001 minus 1.0000, which means 0.0001. The meaningful result is tiny, and any small representation error in the original numbers become large related to the answer. How does this affect your option pricing? Because it affects option pricing, especially when computing these numerically. For example, when I'm trying to find your delta, which is by approximation Vs plus H minus Vs minus H divided by 2H. If H is too small, both option prices are almost equal, and subtracting them creates precision problems, so a trader may get unstable delta or gamma. Next one is your error types. Again, distinguish truncation versus rounding off error. A truncation error meaning is to replace infinite continuous process with finite approximation. Finite example is binomial trees with 50 steps instead of continuous time. When your error is round off error, meaning error due to finite computer precision. Finite example is Monte Carlo accumulating tiny error across millions of paths. In simple word, truncation error is from stopping the math early. Round off error is from the computer not storing numbers perfectly. Error measurement, x is equal to 100, x bar is equal to 98, x is the exact value, x bar is the approximate value. When I have x minus x bar and I take the absolute value of that, it is 100 minus 98 is equal to 2. And relative error is what? X minus x bar divided by x bar is equal to 2 by 100 is equal to 2%, right? Which is more informative, usually relative error, because it tells us the error compared to the size of the true value, right? Then we get into the, again, please focus on relative error, right? Then we get into the question number 4 and 5. We have root finding. The slide focus on algorithms and finance example. Root finding means you have to explain bisection method. Bisection repeatedly halves an interval containing a root. If your FA, FB is less than 0, then the function changes sign between A and B. So a root lies inside. Midpoint is C is equal to A plus B by 2. Then we keep the half where the sign change remains. Why is Newton faster? Because Newton used your slope information, right? In Newton method, what happens is xn plus 1 is equal to xn minus f of xn and f dash xn. Right, because it used the derivative, it can jump closer to the root much faster. Method is bisection. Advantage is guaranteed convergence if sign changes exist. Newton-Raphson, very fast near the solution. Financial example is for implied volatility. Method is bisection. Practical rule is safe fallback method. Newton-Raphson, fast production method when Vega is reliable, right? Question number 5 is role of numerical integration in pricing. Many assets are discounted expectation. So we have V is equal to exponential minus RT. I told you expected risk neutral payoff. We are looking at expected value risk neutral payoff. And the expectation cannot be solved exactly in numerical integration. Approximate it, used in your options for expected payoff under risk neutral distribution, exotics for complex payoff region, for interest rate derivative, for expected discounted cash flow, for Fourier pricing, integral inversion formula. What is the role in portfolio optimization? Portfolio optimization usually requires solving constraint optimization problem. Classic objective has been discussed earlier also, but I'll write down again. It is, minimization of W, right? Transpose of WT, sigma W, just minimize the portfolio variance, but real portfolio constraints are that you have to understand that this value should be equal to 1. Weights cannot be less than 0. And you have to add, you might have a condition like this also where you say that one weight cannot exceed 10%, right? So numerical optimization methods solve what clean formulas cannot, right? And why accuracy is critical in risk management? Because risk system estimated losses, capital and stress result. If errors are uncontrolled, error source, let's say bad simulation, accuracy, possible consequences, wrong war, if you have poor convergence, misleading stress loss, if you have round of accumulation, unstable Greeks, truncation error, wrong derivative pricing, if your metrics instability, poor portfolio allocation. In real world banking, wrong model outputs can affect your pricing, hedging, reserves, capital and regulatory reporting, right? So be very cautious here. Okay, so that's it, guys. That's it for this particular chapter, right? Very interesting lesson, right? You have the detailed solution ahead, you can read them. But overall, I have given you a decent bit of idea. Accuracy is critical because small error in tail estimation can lead to wrong capital allocation. The final big picture, which I want to tell you, is the lesson is really about one powerful idea that quant finance is full of beautiful mathematical models. But in practice, those models run on computers and computers approximate. So a good quant must understand them. Mathematical model, if you have Black-Scholes PD, numerical reality, finite difference rate, if you have expected payoff, numerical integration, or Monte Carlo, if you have optimal portfolio, quadratic programming, if you have implied volatility, root finding, if you're interested in model P, PD simulation, if you have war or conditional war, scenario simulation. The core lesson is numerical methods convert financial theory into usable pricing, hedging, optimization, risk management tool. But only if when we control your error, convergence, and precision. Okay. So that's it, guys. That's it for this lecture. I'll see you in another lecture. But this is easy chapter. Go back if you read it. If you read it twice, also you'll be totally fine. And go back and revise it. I'll see you in the next lecture. Okay. Thank you.